are either things we could give whole talks on or things that my legal department would not let me give a whole talk on. And I'll first be starting off by giving an overview of what Akamai does, talking a little bit about the background, who we are for those of you who don't know, and why we have so many machines. I'll also be talking through the challenges and approaches we've taken to operations and how we operate our network. I'll then be talking through some of the systems we've developed for managing our network, as well as systems we've developed for monitoring it. And finally, talking about some conclusions we've come through our experiences. To start off with an overview of what Akamai does, Akamai has a very large network that's distributed around the world. We have over 28,000 servers now in somewhere around 70 countries and 1,400 locations. And our traffic peaks get pretty significant. On single days, we've delivered as much as 5 petabytes of content to users around the world, and we've had traffic peaks reaching up into the 700 gigabits per second range. The initial services we offered at Akamai were content delivery services, services where we would deliver static websites or somewhat slowly changing websites to users. And this is still one of the cores of our business. And ISPs who look at profiles of the traffic see that we account for somewhere in the range of 10 to 20% of the internet's global HTTP traffic, depending upon where in the world you are. We also have solutions for live and on-demand streaming. More recently, over the past few years, we've been getting into the application delivery space. This means taking websites that are not just static content and not just a bunch of pages that are unchanging, and working on being able to accelerate those to end users around the world. And therefore, we have solutions both around accelerating dynamic sites and web applications. And we also have solutions for edge computing, where we'll dynamically start up Java applications up on machines around our global network and serve content from those Java applications that are provided by our customers. And recently, we've started rolling out a IP application acceleration service where we can accelerate generic IP applications, whether they be TCP or UDP based, to try and get them back to as an alternative to having to build out an expensive dedicated network. Some of the application spaces that we've gone into are all across the board. They range from online commerce to social media to B2B applications. And if you look at some of the list of who our customers are, it's very likely that you're using our service on a regular basis every single day without even knowing it. In fact, if you did know it, that would probably be problematic, because that means that something might actually be going wrong. So hopefully you don't notice that you're using us every day. So why do we need to have so many servers? Why do we have 28,000 servers in these 1,400 locations around the world? And actually, it turns out that 1,400 locations doesn't even include some of the recent things we've been doing, such as recently we put together a deal with Starbucks where we've been deploying servers into hundreds and possibly even thousands of Starbucks stores around the country to help deliver iTunes and other downloads to users' machines within those locations. So the reason why we have machines so distributed around the world is because the internet itself is highly distributed. When you look at the internet from a logical perspective, it's not one big system. It's actually a large graph of interconnected networks. And the connectivity between these networks and the protocols for routing traffic between them is done primarily through BGP. And BGP's goal isn't to try and optimize performance, but rather to allow network providers to enforce business policies with each other and to have the business policies they want. And because the internet is a graph of networks, there's not really a center to it. There's no center to the internet. Rather, there's just a big edge. And scattered around this edge are where all the end users and services on the internet are. When you look at the distribution of where users are on the internet, it turns out that you can't just go and put machines in a few data centers to get very close to a significant portion of users on the internet. In fact, there's no one network that has over 8% of the access traffic. And when you start looking at the distribution of which networks have how much access traffic and where the end users are, it actually trails out over a very long-tailed distribution. In fact, if you want to get out to about 50%, you have to get to the top 30 networks. And if you really want to get close to 90% of the end users on the internet, you have to deploy out to over 1,000 different network providers. So why do we want to have servers in so many locations? Why do we actually need to be out near the edge, and why can't we deploy stuff in the center? Well, first of all, deploying closer to end users gives you better performance and reliability. This is a sample across our number of our dynamic site accelerator customers, where you can see that the performance using Akamai on the bottom is significantly better than the performance of the site without using Akamai. And for some of our customers, this can make a huge difference. For example, in social networking customers, their revenue is a direct function of how many ads they're serving out. And how many ads they're serving out is really a function of how quickly are people clicking through pages and looking at pictures of their friends' cats. And as a result, the more click-throughs people can get and the faster the sites are, the more money those customers get. And therefore, even small gains in performance can have significant impacts on their business. The other reason to have so many machines in so many locations is to really be able to absorb traffic spikes. This is a graph of a portion of our traffic over the course of a Sunday, so it was actually a very low traffic day. And during this, if you look at this little tiny peak over here, that's actually a 25 gigabits per second traffic spike on our network. And if someone wanted to have an event to serve that much traffic, they'd have to build out a fairly significant infrastructure of both data centers, buy a bunch of network pipes, and spend quite a bit of money and resources in actually building out for a short event. And for something that may be an advertising event after a big sporting event, it's not cost effective to build out that infrastructure. So by using our network, which has grown to be the size that it is, they can basically put an event on us with very little or no notice, and we can just serve it without problems. And finally, having servers out at the edge allows us to avoid congestion at network peering points. And I'll talk more about that in a minute. So the reason you want to get machines near the edge for end users is that when traffic is going across the internet and going through commodity links, it's going across a number of paths going between different network providers, and during that, there's actually a fairly significant chance that somewhere along the way, at some frequency, packets are going to get dropped. And when packets get dropped there, because there's a fairly significant distance between the end user and the server they're going to, it's going to take a while for TCP to recover from this and may slow down the performance of sites. By having servers near the edge and having servers that are close to the end user, and then having an overlay network that we can use to get traffic between users and servers, traffic goes over a fairly short path, which has less chance of having packet loss, and if it does have packet loss, the clients can recover from that packet loss more quickly. And also, when we send traffic over our overlay network, we can make sure that we're sending it over multiple redundant paths so that if there is loss, we can recover from it quickly. And also, because we're consolidating lots of end user streams over that, we're able to have TCP connections with very high windows sizes and use a lot of other techniques for getting better performance for users. The other thing I mentioned was about congestion at peering points. Peering points are where various network providers connect with each other, and when you're having traffic going from an end user to a central location on the internet, it's having to pass through a number of these peering points. And those end up being capacity bottlenecks because the financial incentives are not necessarily always there with network providers to go and build those out to the capacity that they might necessarily like. And as a result, if you're trying to distribute content for a very large traffic event from a single location, you may run into congestion problems at those peering points, slowing down how much you can actually get to end users. But by moving machines out towards the edge, it means that we can bypass those peering points and have fewer bandwidth constraints for delivering to end users. In addition to this, we also have services including authoritative DNS, where we have DNS servers around the world. We have a replicated storage solution where customers can host storage on us in a replicated manner. We also have solutions for people managing media assets and solutions for managing for monitoring the performance of applications on the internet. And even processing our own logs is actually a challenge and something we have a fairly significant infrastructure for, because we're handling terabytes of log files per day that we have to process in a SOX compliant manner to go and actually bill our customers. So and the result of this is that we have a fairly significant infrastructure. And having that infrastructure means that we really need a scalable way to manage all those services and machines. If we were trying to do this with something with a traditional sysadmin to server ratio, we'd have a much larger organization that would not function financially at the level that we need to. So this brings us to the sorts of operational challenges we have and the approaches we've taken to those. So the challenges we have for operations is that we have machines all over the world. Many of these machines are in unmanned data centers, or data centers that aren't manned 24/7, and many of them are also, or actually almost all of them are using commodity machines, commodity network links, and are in commodity data centers. We don't own any of our own data centers, and we don't own any of our own network links around the world. In fact, we just buy from other people and use those. And therefore, we're much more of we're almost a software services provider providing this service, and most of our R&D effort goes into developing software to make all of this work rather than into buying and building large data centers and large pipes. And we also need to be able to add capacity quickly around the world. Our growth over the past few years has been fast enough that some weeks it'll come down and someone will say, hey, we should deploy a few thousand more servers in the next 2 months. And we'd like to have a few hundred in this country and a few hundred in this country and a few hundred in this city around the US. And the result of this is if we had to actually send people out there to each one of those locations to do lengthy software install processes and to do administration of them, things would get very messy very quickly. Another thing that's a challenge to operation is that individual faults are happening all the time. There's something we have to expect. When we have machines out in that many locations, many of these data centers are places we have no control over what the temperature of our machines in the racks are. So you may have hard drives fail in large numbers of machines at once, or you may have things just accumulate slowly up over time, or even cosmic rays end up causing memory errors at a rate that when you have this many machines that is surprisingly high. Although it's kind of hard to convince people that's actually the root cause. But these faults are happening at all levels. They happen at the software level, where bugs get introduced into software and gets out there. They happen at a hardware level, where individual parts within a machine are failing, whether it's a hard drive, some memory, its interface cable, or its network card, the local switch, or it may even be that the data center has flooded because of some natural disaster in the area, which has happened to us a few times. And luckily, because we don't actually care about any one given data center, when that sort of thing happens, we just say, oops, that's not good, and go and stuff automatically switches over to another one. And another thing we run into is that QA at this scale really can't catch everything. In fact, the large numbers has some interesting side effects you start running into at this scale. So for example, if you have some development we're making to the Linux kernel causes the kernel, a race condition which causes the kernel to lock up a machine once a year. That sort of thing would be pretty hard to catch in a QA environment. But when you actually put that out to even 20,000 machines, you're going to be having that lockup happen twice an hour or over twice an hour. And if you're having that sort of thing happen over twice an hour, if it only happens once a year on a single machine, and if those are in data centers that don't have 24/7 hands and eyes, things get pretty messy pretty quickly, and you have to be able to have processes that can deal with that and prevent problems like that from fully getting out to the world. Additionally, another challenge we have is that our machines have to be low touch. Many of these may be in data centers where we're working with network partners that don't want to have to be pestered at managing these machines all the time. Or we may have no one locally, and we may not be able to get console access or be able to get machines rebooted within a few hours or days, or sometimes even weeks. So this brings us to the approach we've had to take to operations. First of all, we have to treat failures as normal. We have to treat it as oops, something broke, oh well, and that not actually impacting our customers in any way, and not impacting the availability to our customers and users in any way. When we go and give people tours of our NOC, they oftentimes look at our outer wall, which has a summary of what the health of some of our machines are in some locations. And you'll see that across these they're scattered with little red dots for down machines. And a common reaction from data center managers or sysadmins who are on the tours is looking at it kind of like, if my data center health looked like that and had that much red, I wouldn't be getting any sleep. I'd just be running around all the time. But because for us that's a normal course of operations, we just have to deal with those failures as normal and have a system that can respond to failure. And as part of that, we also need to be able to delay hardware repair until it's convenient. Because in some of these data centers it may not be cost effective to go and repair or replace each box as it fails, we sometimes may want to wait until half a rack in a data center has had some hardware problem over the course of 2 years before sending someone out there to replace an individual machine or to instead replace the entire rack or half that rack at once, or possibly use that as an opportunity to upgrade the rack to newer hardware. We also build a lot of redundancy into our system, and we build that redundancy in at all levels. Almost all the software systems we've built have lots of safeguards at various different levels, so that even if there's a bug in one piece of code, when that bug were to propagate through to something else, it gets caught at the next step. And therefore, we try to make it such that there's enough behaviors to catch things before they become catastrophic. And we build those layers of redundancy in at all levels. We also have a system where we've really relied on engineering building systems in a way such that the systems are actually running themselves. This, in some ways, having heard some of these talks over the past 2 days, a lot of the systems we have are starting to look autonomic in nature. And I was a little hesitant as to whether or not to add that word into the slide when I was pulling these together. But when you actually start looking at this and the level of response and the level of self-tuning that we have, which I'll talk about later, we have a system that does really respond in a lot of autonomic fashions. And we've really relied on engineering to build a system for us. And as part of this, there's a very close working relationship between engineering and operations. And some things that may have traditionally been thought of as operational responsibilities have actually been kind of handed off to engineering so that they can implement that thing. But that actually even puts more burdens on operations, as I'll talk about later. The network that we have is composed primarily of boxes that are not special in any particular way. They tend to be commodity 1U and 2U AMD and Intel boxes. It's a heterogeneous mix of whatever happens to be most cost effective and have the best properties at the particular time when we buy it. And therefore, because we're not buying special magic boxes, we can kind of treat each of these boxes as being somewhat disposable. We take these boxes and we organize them into clusters of machines that are acting in a collaborating manner. And we tend to use machines, the same types of hardware, possibly with very slight variations in numbers of disks or amounts of memory, for both the end user facing services and for various services we have, as well as for our own back-end infrastructure. And this means that if we need some new machines to be infrastructure machines, we can go and take some edge machines and go convert them into infrastructure machines or vice versa. As far as redundancy goes, we try to approach it on many different levels, having redundancy both at the software level, the hardware level, the cluster level, and the overall geographic and network level. And we have both a geographic and network diversity of servers. This means that if any one given network backbone were to fail or go out, we'd have no problems. Everything, both from a infrastructure and edge services perspective, would continue to function just fine. And the same goes with geographic stuff, such that if any part of the world has problems, we can try and route around that as much as possible. For example, during the Taiwanese fiber cut off of China that happened due to the earthquake earlier in the year, our services, after some very short period of time, were able to route around some of that and still provide services to our customers in China, which otherwise were completely unable to get out of country. And we've set this up in a way such that we, at a hierarchical level, so that there's redundancy both within region clusters and within individual machines. So from a fault management perspective, we can either handle individual machines going down and failing within clusters, or we can handle entire clusters or networks going down at the same time. The individual machine failures may be due to anywhere from software to hardware problems, and the cluster failures may be due to hardware problems in switches, hardware problems in network providers, or even, as we've seen in a few cases, natural disasters. For communication between our machines, we try to use multipath communications as much as possible. And we have overlay network technologies so that we're not reliant on any single path working between machines. So and this is both for things where we're transferring customer traffic, but also for our infrastructural communications. The systems we've built for managing and monitoring our network are also using multipath communications so that even if one of our machines at an edge location in some far and distant part of the world can't get directly back to some central controller machine in the US due to a direct path, it can go through an indirect path to go through. So these multipath communications may go through intermediate machines and may send multiple copies at the same time. And one nice side effect of this is that if a single machine along that path or a single network link across that path happens to fail, things can still get through at least along one of the other paths. And this sort of failover, if just by itself, would actually start having problems as more and more machines started to fail. So our autonomic response systems will actually go and kick in and use our mapping system, which I'll talk a little bit about more later, to actually take some of those dead machines out of the intermediate steps so that things will continue to route over a longer period of time between machines that are still alive. And by having multiple levels of redundancy like this, it means that to really get to a point where we're having a serious incident or where things have broken on a significant level, that multiple things have to fail together. And you start to see actually some interesting emergent fault properties when you have a network at this scale, where bugs that you would expect to cause stuff to just not work can actually persist for extended periods of time because other things are catching those problems and preventing them from propagating and spreading and causing more widespread problems. However, this does mean that when you have those sorts of faults, you need to catch them early on because they may not be causing a user-facing fault or an operations-facing fault, and therefore they can accumulate over time into a point where you do end up with multiple failures and you do end up with a case where people notice. So this brings us to what the role of the operations organization is in this environment. The primary role of one of the primary roles of operations is to act as a gatekeeper of operational safety, and to make sure that the way that we're managing our network is actually still in a safe and operationally maintainable manner. Especially if you look at how we've handled a lot of operational things that are traditionally operational responsibilities off to engineering, unless we actually draw appropriate lines, and we as operations and sysadmin people are going and making sure that the things engineering is handing off continue to fit into that same operational model that allows things to be scalable, we'd very quickly find ourselves in a situation of having to manage something we just don't have the people to manage. And therefore, actually being very vigilant about operational safety and sometimes having to make those hard choices and say no is a very important part of what operations does. Another role we play is in configuration and change management. And as much as possible, we've gone and automated this. We've gone and tried to take people out of the loop in configuration and change management. And I'll talk a little bit about that more later. But in other cases, operations role really here tends to be as a liaison to the automation, as the people who are taking the request from the business of, we want to implement this business policy, and then figuring out how to express that in configuration terms that we can then push out and tell the system, and then it can go and execute in some useful manner. So if there's a configuration decision the business wants to make around changing how we're using various capacity or various cost structures in various ways, we can go and operations has the responsibility to go make some of the configuration changes that tune parameters of the system to adjust how those cost parameters are being applied. Another role of operations is an alert response. In this situation, when things are failing or things are breaking, alerts fire in our NOC, and they go and actually respond to these faults. And ideally, in most of these situations, the fault has already been responded to by the automation. So if we have a machine that goes down, things actually respond to it automatically and take that machine out of service. But then at some point, that hardware is going to need to get repaired. So at that point, an alert will fire to our network operations center, and they will go and tend to that problem and look at and try to figure out why is this hardware failed, and if it failed in some way that's not recoverable remotely, put it into a queue of machines that our deployment team will go and replace eventually when it's cost effective to do so. And as part of this, SENOC is also working with operations is working with our network partners to repair both hardware and network problems that get detected. Because sometimes our systems will discover that there is some problem with a local network that they're located within, and so those machines will get automatically taken out of service until whatever problem with the local router or switch can get repaired. Another thing operations has a critical involvement in is troubleshooting unforeseen problems. When you have a system that's this complex, you're going to have things that you didn't expect happen. And as a result, there's a lot of troubleshooting operations does in digging into the root causes of things, trying to understand how some of these software systems actually work, and trying to figure out how various things broke in a way that might have combined in some way to make other things break in interesting ways. The Akamai NOC itself also has a degree of redundancy. We have network operations centers in Cambridge, Bangalore, Reston, and also in San Mateo. And any one of these operations centers doesn't contain any piece of critical infrastructure that we couldn't run the network without. If any of those locations were to have some sort of local natural disaster that required us to evacuate those buildings, the infrastructure that they run on is distributed enough around the world and fault tolerant enough that we could keep running things even without that location. And we could also, if there's a fire in our building, go and take people to an off-site location and continue to do things such as alert response from there. Two areas that operations has to interact with, and to some degree, one of which being customers, the others being network partners. And for our customers, we've really tried to make it such that operations doesn't have much of a hands-on role. We've tried to make it such that operations acts more as in the gatekeeper manner or the troubleshooting things if things have really broken and customer care can't figure it out manner. But as much as possible, we try to make it that the professional services can safely do things without involving operations. We also share our machines across many customers. We don't have individual per customer machines. So if we want to add new customers, we don't have to go and necessarily deploy new machines to support those additional new customers. And operations also doesn't need to be involved in allocating machines out per customers. As far as customers provisioning onto our platform, they can also self-provision as much as possible. We provide them tools within our portal serve application, which allow customers to go in and configure how they want their various services to be working. Or for very complex services, they involve our professional services organization, which does some of that configuration work for them. And in most cases, we don't actually need any operations involvement for going and bringing a new customer online and onto our platform. And for customers to get visibility into into their services, we also have a web portal interface that they can use that provides reporting and provisioning interfaces to their services. And when customers have issues, they escalate to our customer care organization, which provides first-line support, digs into problems, escalates within their customer support team as necessary, and only in the cases that are really impacting multiple customers or where they think that something's actually going wrong with the system, do they escalate over to operations to dig into what's going wrong with the system. The other big interaction we have is with our network partners. And as I mentioned before, the data centers we're putting our machines in aren't special data centers. We don't own any of them. And we also want to be able to deploy machines out there quickly. In many cases, we may even want to take machines and send out hundreds of machines over the course of a month to numerous data centers and bring them all online with very little involvement from operations. So for this, we'll take machines, we'll ship them, we'll drop ship them out to data centers, so they arrive in boxes, and then people within those data centers who either work at the data center or contractors that we may bring in locally within that area will go over to the data center, physically install the machines in the racks, enter their IP addresses at the console, and from that, from that point, we can basically take it from there from remote, from one of our operation centers around the world, and bring those machines up, both in terms of their operating system and their software, without having to have anyone locally do work. And this means we can really rapidly deploy thousands of machines at a time without having to have significant resources locally for any of those deployments. We also use the local hands and eyes for actually, within the data centers, for doing repairs of machines when we want to get a machine repaired, or sometimes have someone reboot a machine in a location where we don't have an RPDU. And in many of our data centers and ISPs where we have machines, they're actually providing those machines to us, and we're not even having to pay for the rack space or bandwidth for those machines. And this is because we're serving significant amounts of content to their end users on their network. And because we can serve that content to the end users on their network, they don't have to bring that traffic in over their peering links with their network providers. So in the end, us having machines in the network can actually save them significant amounts of money. So we really look at the networks that we work with as being network partners rather than necessarily just network providers. This brings us to the systems we use for managing our network. This is broken up into, in this talk, into three main sections, one of which is how we're doing mapping, which is the primary autonomic system we have that responds to faults and directs end users to machines. There's also how we're dynamically distributing configuration out to machines and getting things such as customer configuration files out to machines in near real time, as well as the approaches we take for software installation and installing and configuring software on machines. The mapping system that we have is the primary autonomic system we have. It's this thing that's actually going and responding to faults. It's going and mapping end users to machines. And the goals of it are really to both, first of all, select which machines to send end users to and to find a machine that's both nearby them and healthy to send them to, and to respond to faults as appropriate in those machines. It also goes for our overlay network and selects intermediate machines that we may want to pass traffic through. And for our edge computing applications, we're running Java applications out at the edge, it can go and allocate application servers dynamically and bring up and bring down Java application servers on it to deal with the demand and capacity needs for any given customer. The decisions that's being made, depending upon which level they're at, are being made ranging from every few seconds to every few minutes. And at this rate, given that this is mapping tens or hundreds or thousands of millions of end users, and at that frequency, there's no way you can have human interaction in that loop, or at least without, at a significant level. The mapping system gets divided up in how it manages things into a few levels of hierarchy, and we find that approaching it hierarchically makes it possible to do in a scalable and efficient manner. At the top level, we're figuring out how we want to allocate capacity across machines, figuring out which application servers may want to be running on which machines, which types of content may want to be, and which classes of customers may make sense to serve from which locations in the world. And this is something that has enough business policy decisions linked into it that there are still significant parts of this that we do manually. So there are still a lot of human decisions that go into this, but over the course of time, we're working more and more on automating levels of this, but there's still many levels of this that are completely automated already. At the next level down is where we're mapping end users over to clusters of our machines. And this is being done dynamically in real time once every minute or so. And in this, we're taking end users, finding machines that are close to them and for various manners of closeness I'll talk about. And we're also dealing with faults and handling faults of locations. So if an individual location here would fail, the mapping system would take users that had been mapped to it and immediately map them over to other locations. The next level down is where we're mapping users to machines within clusters. And at this level, we take a bit more into account. We're also taking into account which piece of content they may be requesting or which class of customers they're on to do things to try and preserve session affinity and also to try and preserve cache consistency as much as possible within our machines. Because for a lot of the content, for most content, we don't actually have it stored locally out at the machines. They're cached there so we can bring a new region or a new set of machines up without actually having to copy content onto them first. They can just come right into service and start working. But this does mean that over time, we want to try and keep the same pieces of content cached on the same machines as much as possible. So the mapping system at this level is try to have some level of stickiness and making some decisions around which machines to send people to keep that content consistent. And we also do fault management at this level. So if there's a fault of an individual machine, we can immediately map users over the course of a few seconds to a few minutes to other machines within that cluster. And because this failover is done from one machine to another within a cluster is done via DNS, there are some short DNS TTLs one has to worry about. To bring the availability even higher, we also have a system where other machines within that cluster can actually bring up IP addresses of machines that have failed to respond to faults over the course of seconds rather than minutes. So there we may have a case where one machine fails and another machine just brings up its service IP address and starts responding to users from that 3 seconds later. The mapping system takes quite a few different things into account when it's making its decisions. First of all, it's taking into account the health of individual machines and clusters. It's looking at whether machines are live, down, or suspended. And suspended is this concept we have where a machine takes itself out of service or is taken out of service, but can still continue to serve both the existing connections that are in progress as well as any new requests that may come in while requests are draining out. So a common operational process we may have is that if we want to just take a single machine or a location out of service, we'll go suspend that location, wait for all the connections and end users to drain out, and then actually go and bring the machine down. Another thing we take into account is the proximity of the machines to end users. And this is proximity on different levels. It's proximity from a network hops perspective, proximity from a geographic perspective. And to get some of this data, we're constantly doing network probes on a very frequent basis. We're doing probes into the network, looking for issues with both loss and latency between each one of our clusters and all of our other clusters, as well as each one of our clusters and interesting core points of the internet that we've decided may be interesting to use as approximations for mapping other users within the internet. And as a result of this, we can notice problems such as congested peering links or other problems. So if we have end users who are coming over some link, or if we have machines that are talking to each other across some link, and we notice that link is starting to get congested, we can immediately map around that problem and stop trying to send any users through that congested link. Another thing we take into account is load, demand, and capacity. The amount of traffic we have means that the load balancing itself is a fairly significant challenge. And we want to be able to keep load in our regions as stable as possible and try to actually meet capacity targets such that we're not overutilizing any given region, but that's such that we're also not underutilizing and having machines that are wasting rack space by being underutilized. So we're constantly taking into account the demand from end users, the amount of load in any given region, and the capacity of that region, and have a feedback control system that's going and adjusting where all the mapping goes to move traffic around to keep things balanced. And as part of that, we finally also do take cost into account, where we may decide that for some class of customer who does not really care about how close they are to their end users or don't care as much about it, we can look at that and not serve them from places that are as expensive, and also take different classes of traffic and move them around between different locations to try and optimize for cost. In addition to the mapping system, we also have a number of other things that are effectively autonomic responses to problems within the network. The first one of these is that these machine capacities themselves are self-adjusting. Because we deploy lots of heterogeneous hardware types and also have heterogeneous applications from lots of different types of end users, and some customers may, or from lots of different types of customers, and some customers may go and put an application onto our network that has considerably different performance characteristics from another customer's application, we need to be able to self-tune the system without having human involvement for this. So when we deploy a new hardware type, we don't want to have to go and do lengthy characterizations of that hardware with all the different applications that might run on it. So instead, the systems go and look constantly at their resource utilization, both in terms of disk and CPU, and keep some performance estimators of how they're doing and start to tweak those up and down based upon the load of the machine and feed this back into the mapping system in a closed loop to try and self-adjust the capacity of these machines and self-tune based upon the load that they're seeing. We also have a number of other self-tuning parameters. As, for example, for various connection pools that we have, the actual size of those pools are dynamic, so that the systems will monitor how many connections are in those pools and will start to do things to reduce or increase the pool size based upon the size of the pool. So for example, if we start seeing a connection pool getting too large, we may start decreasing the timeouts for that connection pool to actually start slowly shrinking the pool, but such that we can set aggressively large timeouts most of the time, and only actually have to have shorter timeouts in cases where things start getting large from pool size. As I mentioned before, our system is also monitoring for hardware faults. So machines are looking for, did a disk just fail? Am I having any multi-bit memory errors, or am I having other hardware problems? And if machines start to see any hardware problems or start to see any network problems, such as oops, I can't talk to the router in front of me, then those machines will also self-suspend and immediately take themselves out of service while still continuing to serve and drain out the traffic that had been served from those machines. And even at the back-end infrastructure for the systems that are running our network, whether it's systems that are supporting the NOC or the mapping system itself, or some of our data collection systems themselves, those are also using either things similar to a mapping system or leader election to make sure that they're redundant and can fail over immediately without any human involvement. This brings us to the next part of our system, which is how do we distribute dynamic configuration information out to our network. Configuration information ranges anywhere from system tuning parameters that operations may want to tweak up and down to the customer configuration that specifies how we should be serving any given particular customer's application. And these are things that we want to be able to rapidly distribute out to the network. Depending upon the change, it's something that we may want to be able to distribute once an hour, or it may be something that we want to distribute 10 times an hour, or it's something that we may want to distribute weekly. And some uses of it, as I mentioned, may be allowing customers to configure and change their provisioning information, as well as also distributing some system control messages where the control system itself wants to distribute some configuration out to the entire network on a periodic basis. Two things we run into here, one of which is we have to worry about safety. We have to worry about making sure we don't distribute some config change that suddenly takes down a bunch of machines, because that could be problematic. We also need to figure out how do we do this in a scalable manner and have consistency. So when we push out a config change and some new machine comes back from the dead, it doesn't end up with some inconsistent configuration. The system we have for this, for distributing dynamic configuration, has a configuration repository based on a cluster of machines. And if a client wants to distribute a new configuration file out to the network, it goes and sends that configuration to the cluster of machines, and then that configuration file is distributed within that cluster. And that the distribution of the configuration file within the cluster uses a vector exchange-based quorum system, so that even if some set of machines within that cluster is down, you can actually still commit that change to the cluster. And then when that machine comes back up within that replication system, things will get replicated back into it. So when you as a client are submitting some configuration change into the system, the system will come back either with a, yes, I succeeded with this, or no, I failed at this. And if it actually says that it's succeeded, you know for certain that it's actually going to make it out. And then from there, we use our own CDN technology to go and distribute that content out to the network. So it uses our CDN network, and then and through that, we'll distribute it to our 28,000 machines, or whichever ones may be wanting to subscribe to this particular piece of dynamic configuration. And any one of those machines, if it had been down for some period of time, comes back up, can just refetch that piece of configuration immediately. As I mentioned before, safety is a challenge we also have to worry about here. We don't want to push out some configuration change, have it go everywhere at once, and suddenly cause a system-wide problem. So we have a system which will take a configuration change as an input, push that to a small number of machines, and run some checks on those machines automatically. And it'll go through and automatically run some predefined checks and say, does this change that we made look good? Has it caused any problems on the network of the system? And then from there, it'll go and push it out to a few more machines and say, okay, does it still look good on the network of the system? And then if things continue to look good, it'll continue on and proceed to push that change out to the entire system. And we also have stuff built into this so that if something does go wrong, we can revert back to an older version of the configuration. And if one of these checks were to fail, operations will get involved and looked at what happened or what failed or what broke and can help us recover from the problem. There are more details of this configuration distribution system in a paper we published in NSDI in 2005. The URL for it is actually on the USENIX website. This brings us to the system we use for managing software and configuration in our network. Our goal, and much of what we did for system management here was originally started back around 1999 or 2000, when there weren't many of the tools that existed today. And we realized at that point that it was absolutely critical that you could have systems that you can configure and manage the configuration and software on in a very consistent and reproducible manner. It needed to be something where the configuration state converged towards the desired state, where we as operations and engineering could specify this is the state we want a machine to be in, and that you could then go and put a machine into that state. And we wanted to make sure that things continued to converge to that state. So even if a machine was down or out of service when a previous install went out, when it comes and gets an install 2 weeks later, which may have skipped a few different installs, we wanted to still converge towards that desired state. We also wanted a safe path to be able to roll back releases, so that if something goes wrong when we go and roll out software to the network, we can go and roll back to a previous release easily and in a way that's been tested and in a way that has very little operational overhead. And we also wanted to make sure that reinstalls for a machine were idempotent. Or if the NOC has a machine, they want to just make sure that it's consistent or make sure it's brought up to state, they can just install that machine. And if it's the exact same thing that it was installed with previously, that should be a no-op and should not actually affect the state of that machine. And we also wanted a system that was scalable in the terms of the number of releases that we could get out. We go through and are releasing many software releases to our network every single quarter, and we have a full pipeline of stuff that's coming from engineering through QA into operations and then being staged out to the network over a period of time. And the rate and frequency of that is high enough that we need to be able to support that without having a lot of operations staff devoted to that purpose. To do this, we have a system where a mixture of software and configuration specifies the state of the network. So we have software and some sets of modules that say how to get from how to get to a desired state based upon some configuration, and then we have configuration that's primarily specifying the high-level roles of machines. And the configuration that operations is maintaining isn't going and saying, configure these config files in this machine in this way. Generally, the config file that operations has just says, this machine is a web server, this machine is a DNS server, this machine is this type of infrastructure server, and that everything else falls out from that when we install the machine. And as part of this, we have a very heavy reliance on the software and systems engineering roles. And a lot of things that may traditionally been thought of as systems administration roles have moved into things that are on a very blurry line between what is software engineering, what systems engineering, what is systems administration. The approach that we take to this is that we want to rebuild the desired state of every given machine on each install. And as I mentioned before, we have a mixture of software modules that specify how to configure any given role of machine, as well as a config file that specifies what role should each machine be in. And we take this combination of software and config files, and we package those together into a release, where a release is some configuration, some software modules that say how to actually do that configuration, and then the actual software we're deploying. For any given machine we're installing to, there's a machine state of what that machine is running at that given time before we try and do the install to it. And we want to make it such that even if the install were to fail partway through, that machine state is not compromised. So how we do this is we first of all, on that machine, continue to leave it running as normal, and then have a temporary area of the machine where we rebuild the entire state from scratch. And state here is a specification of what processes should be running, what config files on the machine, what software is on the machine, and we build all of that up for each install in a separate area of the machine. And if while we're building this state up, somehow that fails, we can basically blow away that temporary area, and things will continue, and the machine will continue to work as before, as if we never tried to do an install on it. Once we've successfully gone and built up that temporary area, we hit a commit point. And at that point, we compare the desired state of the system with the current running state of the system. And you may see here in this example that parts of the system are the same and parts of the system have changed. And if we discover that there are changes, then the installation system will go suspend the machine and take it out of service, wait for stuff to die away, and then go and replace the current running state with the new desired state, and then restart everything as appropriate. And then at the end of this, you end up with a machine that's running in the new desired state. Some other benefits of this model are that we can safely, as I mentioned before, we can safely fail while we're building up the temporary state of that machine. So if there happens to be a bug in one of the modules or a configuration error that doesn't make sense, we don't end up with inconsistent machines or bring machines down during the install. We also have the same configuration model for managing both our Linux machines and our Windows machines. And this even means in many cases we'll have a software component that'll run both on Linux and Windows, and have some set of configuration modules for installing it that work the same both on Linux and Windows and have slight variations based upon, do I want to configure a Windows machine in a slightly different manner from how I configure a Linux machine. And we also have a system set up where we're using this technique. We can remotely re-image and switch machines between OSs. So if we want to switch a machine from a Linux machine to a Windows machine, or vice versa, we can do that remotely and in a fairly automated manner without having to have people go and touch those machines locally. This model also gives us consistency even as machines are changing what roles they're running or what components are on that machine. So if we add or remove software to machines, when we go and install the machine, the new software will get started up and the old software will get brought down. Or if we change the role of a machine, which may change lots of components that are running on it, that machine will consistently converge towards that new desired state with that new role. Another side effect of this model is that it's easy to deterministically roll back a release. If we go and roll out some software and we discover there's a problem with it, either partway through or further, we can actually just roll back the release. And to do this, we just go and take some previous release that we've done that we know is successful and install it on the network. And then the network will converge towards that previous state that the network had been on, and we've now successfully rolled back whatever release was on the network. And because we don't actually have to write specific rollback scripts or have people go and say, here's how you actually roll back the network, and we just install with the old version, it actually makes it much more consistent during those rollback scenarios. And you don't get into a case where, oops, there's a bug in the rollback script and now we're stuck with the new release. Another benefit of this model is that it enables reproducibility between our QA, staging, and production environments. When a developer is working on some software and they're using the same tools for maintaining the machines in their development network as we're using in production. So they can install a machine using the same stuff and it'll converge exactly to the state that they want it to. And then they'll hand that off to QA, and the QA group can go and install that software onto their set of machines and test it. And then when we go and get that software label and want to release it out to the production environment, we know that it's exactly the same as what's been tested in QA and tested in the development environments. One of the challenges of this model is that it doesn't work quite as well as one might like when there are lots of different types of machine roles. Each time that we actually want to introduce a new role or service, it does mean that the software engineering organizations have to do some systems engineering work on how they're going to take that new service and that new component, integrate it into this model, which means that it's been tricky to go and take things that have lots of little one-off types of machines and get it working well within this model. However, in the cases where we have gone and done that, we've actually discovered that there's enough benefits to even things where you have one-off machines that it's still worth moving them over to this model as resources permit. This brings us to the systems we use for monitoring the network. The primary system we have for monitoring and collecting data about what's going on in this network is a system called Query. The Query system allows us to collect information from all across our network in a real-time manner and get a good real-time view of all of the things within our network, whether they are software components, a network device, or a machine. The model that we use for this is a relational database model. So we pull all of this stuff in real time into this real-time relational database. And that allows us to actually issue queries that combine facets of information across the network. So if we want to know, ask some question after the fact of how is this machine interacting with this other machine, or how many machines do we have that have this hardware type, that have memory usage of this process within this range, that have a CPU utilization over some percentage, it becomes very straightforward. Just write a query, run it across the entire network. It may be combining information from multiple machines within a cluster, multiple machines within a network, static configuration information, and allows us to look at stuff all across the board easily. The data collection system here is itself multipath and fault tolerant, so that if one of our machines in a remote location can't talk to all of the internet, it can still actually report information into the system by reporting it through multiple different paths. The interface we have into the system is a SQL interface, which is a convenient interface for relational databases, where people can just write SQL statements that combine information from multiple different parts of the system and merge them together and get responses back. Our philosophical approach here is to really report all the data we can from the edge. We try to instrument as many software components as we have. For third-party software components, we write adapters that go take information out of them and report it into the query system. And for local network devices, we have agents running that are collecting information from those network devices and reporting it into the query system. And our goal is to try and report as much information as possible and to not make predispositions on what is this data going to be used for when we're reporting it into the system. Because oftentimes when you're rolling out some piece of software and figuring out what you want to report on, you don't know at that time what sort of questions you're going to want to ask. And oftentimes going and getting changes out to provide new information takes long enough that it's easier to just get as much information reported and then allow operations and engineering to filter on that and figure out what's interesting ad hoc and after the fact. The query system has a model, as I mentioned, which is a relational database model, where various processes and agents running on machines out of the edge are table providers. And each of these table providers will provide some set of of tables into the query system. And these tables will each have a name, and like tables in a relational database will have some set of rows and some columns. So in this example here, each of the machines is reporting for each of its network interfaces what the IP address of that network interface is, what the name of that network interface is, and how many bytes and bits are being received per second on that network interface averaged over the past, let's say, 5 minutes. And these table fragments are going to be reported from all these different table providers around the internet. The query system then collects these tables from all of these machines and aggregates them together into a single table centrally. And from this, you'll see that the rows from this machine and the rows from this machine and the rows from any of the other machines that are reported are all going to be available in that table. And then if you want to run a query against it, you can run a query against the aggregate data. So in this example, the SQL statement goes and says, I want to add up all of the transmitted bit rate from that network info table where the network interface is ETH0. And that gives you the result of, across all of those machines, what is the total amount of bits per second being transmitted at any given time. The query system, at this point, we've instrumented enough different services that we actually have 1,400 different tables being reported into query. And the total amount of data in this is now up to 70 million rows. We have a few individual tables which by themselves contain over 3 million rows. And this data is being reported from most of our software components, as I mentioned, whether it's our components, third-party components we've written adapters for, or network agents. And the cycle time for updates for this data is in the 1 to 3 minute range, so that somewhere on the order of every 2 minutes or so, you have a fresh new version of all of the state of the entire network in real time and what it looks like. In addition to feeding dynamic information into the system, we're also feeding static configuration information into the system. So we take all the global configuration around what roles machines have, what various contracts do we have with different network providers, what customers do we have and what services do they want, and feed that into the system as well so that we can join both the real-time data along with the static data of what we think the configuration state should be. In order to get a system that can scale to this point and have 70 million rows being updated every 2-ish minutes, we've had to do a number of optimizations. For example, we've had to do stuff where we cache strings and have any given string exist only once in the system. And we also have optimizations around sending diffs of data. So if there's things that are unchanging, such as the amount of space used by various config files in some directory, if that's not changing on a frequent basis, we're not going to be sending at each update frequency. We're just going to send what's changed. We use this query system for a number of different roles, monitoring roles within our environment. The first one we use it for is alerts for fault monitoring. This is the primary way that the NOC knows that something's wrong in the network and can go respond to it. And for this, the NOC has somewhere on the order of 2,400 different alert definitions, where each alert definition is a little bit of SQL code someone's gone and written looking for some predicate or invariant on the network that we think is interesting and that we want to match on because it might indicate some problem. And these alert definitions drive many of the NOC workflows. There's something where an alert will fire in the NOC saying this is wrong on this set of machines or this is wrong globally across the network, and they'll go and ticket that problem and then start following an associated procedure that says what to do when that alert fires. And then that alert will be associated over with that ticket, and there's a two-way connection between the ticketing system we use and the alerts that are firing. Another use of query is for diving into system behaviors. Because the system is so complex, it's really hard to get a feeling for what's actually going on in it. And as part of this, we need to really be able to understand trends and correlations of what's going on, how various things are interacting with each other. And one of the best ways to do this is to have nice little pretty graphs that show how various things are looking over time. And from this, we have around 8,000 different graphs feeding from query data, where someone has written a SQL statement that says, I want this slice of data reported in, fed into an RRD database for every one of the rows that it returns, so that we can go generate graphs from that. We also use the query system for real-time load and traffic reporting. So if we want to see what the load on any given region is, what the load from any given customer is, what the load from some combination of customers are, we can go, or even what the load from some customers and or from one customer in a geographic set of the world is, we can write some SQL statements to combine that together and give us real-time reporting. And this goes and feeds into our capacity planning and capacity management, where based upon that load and traffic reporting, we can figure out which parts of the world we may want to go and deploy more servers into. And the query system is also used to collect data that's used for some control systems, such as the system for distributing dynamic configuration state out to the network, where it'll get data back from query to make a decision on does the network look healthy or not, and use that for success or failure in making decisions on whether or not to continue propagating changes out. It's worth noting that many of the real-time systems like mapping need faster cycle times and, in some cases, larger or more specific amounts of data, so we have other data collection and data transport systems that those use. As I mentioned, one of the uses of query is for alerts and firing alerts into our NOC. For this, we write a SQL statement which is filtering for some anomaly, maybe looking for some problem or over some set of machines or on an individual machine, and we then present those alerts into the NOC where they can be taken and responded to. The alerts themselves are SQL select statements. So here's an example one someone may have written, where they're saying, I want to go and this one is asking this question of what are on all of the machines that have the role DNS, which of those machines are using more than 75% of the available system memory for the resident set size. So in this case, they're going and taking two tables, one of which is the sys table that says how much memory is in a machine. Another one is a processes table that has a list of all the processes and all the machines. And from that, it has the resident set size of all those processes. And it's combining those two together, and then also filtering out where only is looking for machines that are in where the role of the machine is to be a DNS server. And from this, it makes it very easy to write these little statements that are making assertions about things that should or should not be true on the network that should be responded to. And as I mentioned before, these are oftentimes combining static information, such as what the roles of machines are, with multiple real-time data sources. Another use we use query for is for real-time trending of data. And for this, we run a SQL statement frequently, and we feed it into a RRD, or round-robin database, using our RRD tool. If you're not familiar with it, you can look online for RRD tool. And from this, we can generate lots of interesting graphs on various topics. So for example, this one might be a graph of capacity, of load versus capacity for some subset of things. And and you can see the daily periodic fluctuations for that class of traffic. And this one might be a breakdown of the health for a subset of machines, of which machines are in one state, which machines are in another state, which machines are on a third state. Here's another one that is, or both of these are some periodic traffic where you can see, based upon some class of traffic, such as customer breakdown or some other geographic breakdown, what the level of that traffic is. And that also has a periodic daily fluctuation. Or in this example over here, there might be some system parameters such as CPU utilization, memory utilization, averaged across the system, where some of them have daily fluctuations and others are fairly constant. And we have a culture where in the operations organization, we'll organize a lot of these graphs into pages that contain interesting bits of data that we think are good summaries of various services. And we'll look at those both while rolling out new software. We can look for trends of, is the software changing the characteristics of the network? Or we can look at it from a does stuff look healthy? How might we want to change? How might we want to go and make changes to keep improving things, get better costs, or more capacity in various areas? So the uses of this both go into real-time monitoring of traffic levels, as I mentioned, also into understanding system behavior and understanding trends, and also into capacity planning. One thing that's very interesting from this is using this for finding memory leaks. If you have a process that's leaking memory over time, you'll see it very clearly on a graph that shows its memory utilization. You'll see some sawtooth where the memory usage of that process will slowly grow over some period of time, and then when that process hits some limit and gets restarted, it drops back down and then just has this nice little sawtooth curve over some period of time. So this brings us to some of the conclusions, some of the things we've discovered from our experiences with this. First of all, for running a network like ours, we found it critical to design for failure. You need to just assume that things are going to break and assume that you're going to have faults and assume that you're going to have faults at all levels. And as a result, you need to build systems that are redundant, build systems that have as much fault tolerance in them as possible. Build systems such that when you're writing some piece of software, that software, even if some input to it fails, it will still be able to recover from that. Or even if it fails, the next thing in line is not going to go and fail subsequently. We also need to have automation, autonomics, and more automation to make things run as smoothly as possible. A lot of the things we do are things that if we had people having to do them would either take too long, would be too cost effective, would require too many people, or would result in us giving people jobs where the only thing they can do is just keep doing some boring, repetitive, risky task over and over again, which no one notices until they make a mistake, in which case they get noticed by upper management. And we'd want to kind of avoid states like that. And as part of this, we need to avoid making manual changes. We need to avoid bypassing the model of the system and saying, oh, I'm going to go tweak this thing on this one machine in this way outside of the model. Because as you start doing that, although our system will try and converge it back towards the desired state, you have more and more things that you need to track and keep track of out on the network. And those sorts of manual changes are going to be inevitable, and they will happen. So it's critical to have good processes to track them and manage them to make sure that they're not too frequent, but such that when they do happen, we know which machines they're on and where they are, so that we can avoid causing problems due to them. Another thing we found critical is having a deterministic software management system, having something that's managing the configuration of machines in such a way that it converges over time to our desired state, and such that if we want to roll back a release or make some change to a machine, or machines are disconnected from the network, or are newly introduced and get a fresh install versus have been running for some period of time and getting incremental installs, that they're all converging towards this desired state. And as part of that, being able to roll back stuff safely has also been critical and has saved us many times. Another thing that's critical here is when you have a systems at this level of complexity, you really need good tools for understanding the system behavior. Unless you as a system operator can have the foggiest idea of what's going on in the system and be able to dive into and ask questions about various slices of system behavior, it becomes very unmanageable very quickly. And through the query system, we have a system that works pretty well for being able to combine things together and ask questions and get a good understanding of things that are happening, especially when things are breaking. So one thing that seems to be a common slide on a lot of the talks here is what is a world where we have lots of automation of this mean for systems administrators? And based upon our experience, we found that there's really not doom and gloom in the future. There's certainly going to be important and probably ever more interesting jobs for people in systems administration roles. First of all, not everything is cost effective to automate. There's always going to be some new thing, some new idea that someone came up with. It just doesn't make sense to automate, or there's some small business workflow that should be done in a traditional manner, in a traditional way. Secondly, in a system such as ours, the role of a sysadmin becomes more and more critical in bridging this world between engineering and operations. especially because the line between engineering and operations gets very, very blurry and more blurry over time. That bridging role and acting as an advocate for the network safety becomes critical. And also acting as a consultant, because oftentimes the operations folks really understand the whole system much better than the engineers do. You have an engineer who is focused and understands some little software component and how it works, but the operations organization can generally has a much broader vision of what's going on and can act as consultants to those engineers as they're doing work. And as part of this, it's also critical for operations to have early involvement in the design process. For the past however many years I can remember, I've been a member of the architecture board at Akamai, and my role there has been to, as we're reviewing the designs of all of our systems, to make sure that those systems are being designed in a way that they're redundant, fault-tolerant, scalable, and also operationally maintainable. And we regularly will have engineers come in and say, oh, I want to design the system in this way, and have this thing where, oh, because it'll only happen infrequently, operations has to go and do some manual tweaks each time this scenario comes up. And as operations, it's been critical for us to go and say, no, you can't build it that way. You actually have to go and do it this other way so that it is maintainable and it is scalable and it does fit within our model. And as part of this, operations is also acting as gatekeepers, going and sometimes saying no and working with the business to make hard trade-offs, of saying that hey, going and doing this thing is not safe at the moment and is not a good trade-off to make, because it may, even though it may be critical for maintaining this one customer, it may have too high of a risk of endangering these other customers. Sysadmins and operations are also in a critical location for identifying scaling limits. As you have big complex systems like this, you're always going to engineer them to some scaling target. And when you've engineered them to that scaling target, it may not be for another 3 or 5 or 10 years, but eventually you're going to start getting to a point where growth makes it such that system is no longer really scaling and working well. And sysadmins and operations are by far in the best position to realize when things are in that state and to act as an advocate within the business to make sure that engineering work or operations work or other work is done to address those scaling limitations. And then there will always be problems that slip through the cracks, especially with complex systems like this. There are going to be things that break. There are going to be software that behaves in unexpected ways, and there are going to be interesting things to dig into and troubleshoot. And as part of this, our jobs become more and more understanding how these complex systems are working and becoming people who really understand how is the system as a whole working together. So that brings me to the end of my talk. For more information about us, you can go to our website at www.akamai.com. On our corporate website, we also have a list of technical publications, including some things on our configuration management system, and as well as other things that our research group has published. I think we also have a paper on our reliability model and some of the approaches and philosophies we have on reliability and availability. And yes, we are also hiring. You can either go to our website or you can visit us down in booth 313 if you're interested in looking. Thank you.
Are there any questions? We have a nice microphone up here waiting. I guess that's it. Then lunch is on your own. Thank you, Erik.